Hello students, myself Devesh Prabhakar. Welcome to Process Control lecture series. In my previous lecture, we discussed about the integral control mode. So, in this lecture, we discussed about the derivative control mode. So, this is the last one type of the continuous control mode. That means we know there are the three types of continuous control mode. First one is proportional, second one is integral, and this is the last one, the derivative control mode. So now we start the derivative control mode. So in this lecture we discuss how the derivative control mode operates and what are the applications of derivative control mode. So we start. Suppose you were in charge of controlling some variable and at some time t0, your helper allowed the error is 0. That means there is a one situation. Suppose you are the in charge of one controlling system and your helper at the time t is equals to 0 allowed, let us say the error is 0. What action do you want to take? What action you take? Of course, no action. Well, it would seem perfectly in relation to answer none. Because we know already the error is 0. So why we have to take the action? Because after all the error was 0, so we do not require to take any action at that time. But suppose you have a screen that shows the variation of error in time and that it looks like a figure. See, this figure indicates. So the output of your system is look like this figure. So here you can clearly see that even though the error at t is 0, it is changing in time and will certainly not be 0 in following time. So from the graph you can understand at time t is equals to 0 the error is 0, but in the following time the error will not be 0. So you require some controlling action. Therefore some action should be taken even though the error is 0. This scenario describes the nature and the need for the derivative action. So that's why we require the derivation control mode or the derivation action. So this is the importance of derivative control mode. Derivative controller action respond to the rate at which the error is changing, that is derivative of the error. The analytical expression for derivative control mode is given by Pt is equals to Kd into dep by dt. See, this is the analytical expression for the derivative control mode. We know the analytical expression for the proportional and integral mode. So this is the analytical expression for the derivative control mode. So here you can see this is a d by dt to ep. So that's why this mode is known as the derivative control mode. Here this Kd is indicate the derivative gain and Pt indicate the your controller output. Derivative action is not used alone because it provides no output when error is constant. So this is the limitation of derivative control mode. So we cannot use alone derivative control mode. So we can use derivative action with integral action or the proportional action. Because when the error is constant, so at that time the controller output becomes 0. Because here we derivative the error, that means here the EP is constant. So we know the derivation of constant is what? The derivative of constant is 0. So that's why here we get the controller output is 0. So we cannot use the derivative control mode alone. Derivative control action is also called rate action and anticipatory control. So it is also known as the rate action and the anticipatory control. Now we understand operation or working of derivative control mode by help of this figure. Figure illustrates how the derivative action changes the controller output for various rate of change of error. So here you can see in the graph 1, that is upper portion of the graph indicate the variation of the error, and accordingly that we get the output of the controller. So in the below graph you can see the output of the derivative control. So now we understand how it works. For this example, it is assumed that the controller output with no error or the rate of change of error is 50%. That means here we consider the controller output is when the error is 0. So at that time the controller output is 50%. So here we indicate the line. When the error changes very rapidly with positive slope, the output jumps to a large value, and when the error is not changing, the output return to 50%. So here you can see when the error changes rapidly. So when error changes rapidly positive side, so at that time the controller output produce big, that means large output produce. You can see here the first peak indicate that, and the second and third number peak you can see the area between the third number. So this at that time the error is constant. So the output return to the 50% value. Now opposite side we discuss. Finally, when the error is decreasing, that is negative slope, the output discontinuously change to the lower value. So we can see when the error is become the negative. So at that time the output discontinuously change to the lower value. So this is the operation of the derivative control mode. The derivative mode must be used with great care and usually with small gain, because a rapid rate of change of error can cause very large suddenly change of controller output and leads to instability. So this is the limitation of the derivative control mode. So that's why the derivative control mode must be used with a great care, because when we operate with the small gain, and we have to operate with the small gain, because when the gain is more, the rapid rate of change of error can cause a very large sudden change of controller output and leads to instability. That means it not work in a stable region. it create an oscillation. So this is the limitation of derivative control. So we can use derivative control mode, but with small. Now we summarize the derivative control mode action. So if error is 0, the mode provides no out. This is the first 1 point of summary. In the derivative control mode, if error is 0, then the mode provides no out. If error is constant in time, the mode provides no out. We already discussed in the second slide. We know the output of derivation of constant is 0. So here we get the 0 output of the controller. If the error is changing with time, the mode contributes an output of 80% for every 1% per second rate of change of error. So if the error is changing with time, whether it is a positive error or negative error, the mode contributes the output of 80%. 80, that means the gain of this derivative controller for every 1% of second rate of change of error. For direct action, positive rate of change of error produce a positive derivative mode output. We already know what is direct action and what is reverse action. So for the direct action, the positive rate of change of error produce a positive derivative mode output. So this is the summary of proportional derivative control. So in this lecture, we discussed about the derivative control. So this is the last topic of continuous control mode. We already know which are the type of continuous control mode. There are basically 3 types. First one is proportional, second one is integral, and third one is derivative. So this is the most important topic as per the GTU, because in the GTU many times question asked in a paper like explain the proportional control mode, or explain the derivative control mode, or what is the integral mode, what are the advantages of derivative control mode, or what is offset. So this type of question asked in a GTU paper. So as per GTU point of view, these 3 modes, that is the proportional, derivative and integral, is most, and also ask the example based on this mode. We already discussed example in proportional and the derivative. So this lecture we discussed the derivative. Thank you.